Okay, I started the recording. So let me first start into sisHYD. There is a desktop icon. Just double click. It will start up MicroStation or one of the MicroStation products and integrate with MicroStation. sisHYD is a V8i product, so it can integrate with the various MicroStation Select series. We recommend Select Series 2 and higher. In the meantime, we are on Select Series 4. The main menu of sisHYD is integrated in the MicroStation menu, and that is where you get access to the software. It's via the sisHYD menu here inside. From the sisHYD menu, you get access to the most recent projects. You can create new projects, open the project manager to look up existing projects. One functionality that may be interesting for the beginner is we have sample projects. If they are not installed or updated, you can just click this button, and afterwards when you go to the menu, you find sample projects we created and we ship with the software. And from the names, maybe you see what they are about. It's about operating with 2 supply stations, with admixture control, a cooling network, consumers from return. So it's this is from feedback we also got from users, what they want to do with the software. So we created very small demo projects and they ship with the software. The other ones are more special. I will skip over them right now. Okay, I have here prepared a district heating demo, and I will open this project. So I pick it from the most recently opened project list. sisHYD will now open with the UI. And maybe first how you get help. We have an online help and the sisHYD help contents. So from here you get into documentation. The online documentation is what we ship with the PDF file, so it's identical. The help, you can navigate directly to it, or you can get context-sensitive help. So whenever you in a dialog box, like here, and you press the F1 key, we open the help and show you the associated chapter. The software is oriented towards the workflow. When you create a new network, after creation of network, you set up controls and the network computation. So first is here, file menu is about creating and managing projects. Then you have the typical edit menu, followed by components. Components are the elements that make up the network. The components menu is then structured into the real district heating elements, nodes through customers, and then some template types. Those types like pipe types and pump types, it models the a pipe type with the inner diameters, the insulation coefficients, and so on, to avoid entering the data over and over again. Instead, you create a pipe and you assign it one of those types, similar to pumps and to valves. Once the network has been constructed, most likely with the graphical tools in the graphic UI, then you would set up controls and use the controls within steady-state computations. You run computations. After running them, you will probably want to report on results. Reporting with HTML reports. Another sort of reporting would be using the graphics and color code graphics. And that is what the drawing menu is about. And in district heating, some users also use profile plots to indicate the pressure difference between supply and return, and to check if the system, how the system operates. Yeah. Okay, the graphical tools are divided into we have several toolboxes. One is about the construction of the network, so you can create nodes, pipes, and the elements that make up the network. There's the wrench to edit an object, to access an object. So when I click the wrench tool, I move here into the graphics. Sorry, I activated the tool. When I activate the tool, it is highlighted to signal this is the active one. From the status bar, you get a feedback. So it tells you, please identify the element. And the operation we are going to perform is we want to edit. So I move onto a pipe. It's highlighted. And when I click, the associated dialog box is opened. So that is, I think, one of the most important operations to access the element data via the graphical UI. When you open such a dialog box, you will notice there are two boxes that actually open. One is the list of all pipes on my right-hand side, and the individual pipe dialog you selected. So I picked pipe, which was labeled KO35, KO95. This is the dataset with the dataset label at the top. And here is the data of the pipe, the construction data. It's connecting node KO35 with node KO95. It's assigned the zone labeled name, main. And below we have the data for the supply in one column and the data for the return in another column. Typically for district heating systems, those columns are almost identical. So with the diameters, typically they are paired, but you are free to modify the diameter only on the return. Maybe I show this. If the pipe should no longer be symmetric, you can uncheck this box and now modify the return diameter, for example, to a DN80. If I do so, you see now that columns supply and return, they are different. In case you check the symmetrical again and you modify here on the right hand, let's say to DN125, we automatically do this for the other pipe. So that makes construction and maintaining this information a bit easier. The standard case is that it is symmetric. sisHYD allows to also have a pipe just in the return or in the supply. To do this, you would uncheck the return, which means now the pipe element is only in the supply. If I do it the other way around, it means it's only in the return. If you want to uncheck both, it will not let you do this. In the status bar, you see here an error message about the operation. It says, cannot clear all network positions of a pipe. Please choose delete from the dialog box to get rid of the entire pipe. So deleting is a separate operation with the tools. I can show the tool in a second, or I do this here. In the modify toolbox, we have a delete function. So this really gets rid of the pipe. So if I choose delete, the pipe goes away. With the edit undo operation, you get the pipe back. Okay, so I go back to the construction tools. So under construction and modify, you find the wrench tool.
Minor loss coefficient.
That's the some say zeta value. It's the English term is minor loss coefficient. It is the friction you have from mounting parts in pipes. We compute the pressure loss of a straight pipe, and the pipe is typically not straight. There are bends inside, and you can assign the minor loss coefficient to bends, and that accounts for this bending and that it's not a straight pipe. Some people maintain this information. Others use statistical data. So if this is a straight pipe, we know all pipes have a certain amount of bends. So we do not compute with the pressure loss of the straight pipe, but we increase it by 10 or 15%. And this accounts for the mounting parts and for all these bends inside. If you want to use it, one method for it is here on the fittings tab. So it is for fittings for mounting parts. You can add here, I can create a new, let's say it's a 90-degree bow. You give it a drag coefficient or a minor loss coefficient. I don't remember the number. We have just, I note from one user who is doing it because it's quite a lot of effort to do it. Most users use the statistic, but if you have this one, you add it into the dialog box. You can give it the number. I want to have 2 of them in the supply, 1 in the return. And now 2 times 0.5 is 1. 1 times 0.5 in the return is 0.5. Let me go back to the general tab page. And now you find this fields grayed out. And we compute the sum of the minor loss coefficients for you. And they make it into the computation of the pressure loss for a pipe. So you can use this method, or if you remove them here, you are free to enter a value here if you know it.
Like 1.2 or 1.15.
Yeah, it depends on the number of bends. There is literature that tells you how much what the drag coefficient for such a bend is. We do not ship libraries with this SisHYD, but yeah, because almost no one is using it. We know it from the East Berlin networks. They use it. In West Berlin, they do not do it. And the main reason is it is quite a high effort when you build up a network to provide all this data. The main method used by most of the users is under components, zones. Under zones, we have a length correction factor. And if the factor is 1.0, it means that you just compute the pressure loss of the straight pipe. You put it to 1.1 or 1.2 to account for all the bends. So that is statistics. If it's a very dense network, maybe you have more bends. If it's a transportation line, it is different. And if you do the computation and it does not match your reality, you may want to change length correction factors. So maybe for a transportation line, you introduce a different zone. And for an area with a lot of consumer stations, you build up another zone. And then you can operate with different length correction factors for each zone. That's the motivation behind. And when we are talking about pressure loss computation, there are different methods to correct pressure loss. One is this length correction factor. Another option is the wall roughness, because that influences the Reynolds factor. And if you want to adjust your model results with reality, you can choose the length correction factor, or the alternative is the wall roughness. Whatever suits you best and whatever makes the best synchronization from model results with reality. There are similar factors to compute correction factors here for the heat transfer. So for the heat loss. Maybe we can discuss this first. So on the pipe, you specified the pipe type. In my case here, it's a DN32. Let me edit the pipe type, or let me go to the pipe type by right-clicking on the pipe type field. You get a context menu with Edit Dataset. It's important to click on the pipe type with the mouse. If you click on empty space here, you get the dialog box context menu. If I move the mouse onto an element, I get the context menu specific for this element. So for these drop-down boxes, we have a context menu that lets you open the associated data set. So with Edit Dataset, I get to the pipe type and the data which is behind such a pipe type. In this case, the label is DN32, but the nominal diameter is standard. It is 37.2 millimeters. It has a thermal coefficient, which describes the heat loss, the wall roughness, and pressure rating. And I move it a bit over here. In the zone, you find the correction factors that apply here to the heat loss computation. So we correct then the heat loss computation with how do I call it in English? One is a factor, one is an additional part. So maybe I go to the whiteboard or I look up the formulas. I think in the online help it's described. Okay, it's too small, but it's the length of the calculation. The length dependent correction is the length of the pipe times length correction plus there is a factor which is diameter dependent. So those are the factors you found here. Sorry, it's in the pipe type. Sorry, the zone here. So there is a length correction factor, and there may be a factor that that depends on the diameter of the pipe. And this is the formula to compute the effective length for the pressure loss computation. So typically, if you do not do a diameter dependent length correction, the factor is 0, which is default here. So which means if this is 1.2, it's the length of the pipe times the factor, in this case 1.2. So you increase the pipe length of the straight pipe by 20% to account for the additional pressure losses caused by bends. Okay, further down, that is the way how we correct wall roughness. So the wall roughness in the computation is the additional part. You can specify in the box, it's here, it's 0, the additional part, plus the wall roughness from the pipe type, it's the 0.15, times the factor. Here's a wall roughness correction factor, which is 1. So this is set up to not correct via wall roughness. So given the situation here, we effectively compute with a wall roughness of 0.15 millimeters. If I would put here 1 millimeter, the computation would be with 1.15 millimeters. And if I use here correction factor of 2, then it's 1 plus 0.15 times 2, it's 1.3. Pardon?
Can you say me, okay?
Yeah. Okay. Let me use the whiteboard in this case. So the wall roughness in the computation, in the calculation is wall roughness, the additional part, plus wall roughness from pipe type, times, and then the wall roughness is the correction factor. This is the correction factor. Yeah, we have a report for that. So when you did a computation, you can get a report for the pipes with the wall roughness and what effective values we have used to look up what really happened. But this is a good question. It's important to know what happens in the system and why it happens.
How about diameter and
Yeah, it is. Yes, it is similar. That was the one above here. I also go to the whiteboard and put the formula again. So the length in the computation, in the formula, L for length, is the length of the pipe times, and now it's the factor, correction factor. It's 1.2 in our example here, times, and then it's the factor, it's a plus factor for correction for the diameter times the diameter itself. So if you have a factor, you would account for larger pipes. So larger pipes would get a higher correction than smaller pipes. Right. Those are just factors to get the model results in sync with the reality results, which means you have to have data and measure pressures and flows, if possible, at the constant state of the network. So if you have a lot of load changes, there are a lot of unsteady, if there are a lot of state changes in the network, that's not a good point in time to try to adjust the network results. because there is a lot of insecurity about flows, and so it's I think you can do it for the main pipes in situations where there is almost constant load, and then you have reliable pressures and flows, and then with the computation you know how to correct your flows.
Can you start just
Yeah.
첫 번째는 밴드랑 두 번째는 The first one is about calculation by band, right? The length correction factor is
Yeah.
calculation band, and the second one.
This is if you do not want to use bands, you would use this factor, right? And the second one is this is an alternative. If you find your computation does not match reality, you want to use this factor, or maybe you want to adjust wall roughness, because when the pipe gets older, the roughness changes. So it really, and it can help to get your computational results in sync. And similar with this diameter dependent correction, I never heard that someone is using this factor. We have it inside. It's a method to get the results in sync.
So you mean no one used the dynamic factor, right?
I do not know anyone who uses this one, but I know in the past there were a lot of discussions which way is the right one. Use the roughness or use the length correction factors. So both methods are applied by users, and some favor method 2, one favor method 1. So our software allows to use both. You can mix them, but the preferred method I know about is almost all users use the length correction factor because it's easiest to apply. Unless you have maybe measured data you can compare.
Yeah. 그러면 답은 필요 없을 수 밑에 걸로 Okay, so we are gonna use the length correction factor. Is that okay?
Yes, that's okay.
Yeah, we're gonna don't use the
wall roughness.
wall roughness.
Yeah, that's okay.
No problem, right?
No problem. I know that the district heating organization in Germany, they have statistics, and they tell, okay, this factor is between 10 and 20%. It depends if it's transportation line, it's a bit lower. If it's an area with a lot of consumers and a lot of bending of pipes, it is higher. And yeah, if you really do this comparison between measured results and the computational model, what I learned from one of our users is it is most important to get the heat loss computation correct. And the reason behind is that maybe you can write again a formula. One of the most important formulas is that the heat load is the mass flow times the heat capacity times the delta T. It's the temperature difference between supply and return. And so if the heat loss along a pipe is a bit higher or lower, the temperature difference changes.
Yeah.
This is then linear with the mass flow, but in terms of pressure loss, it's square. So the pressure loss, delta P, is proportional to the square of the mass flow. So this has then quite a significant impact on the pressure loss computation. And he said that he had ready to adjust the heat losses for the network, and once the temperatures were okay, he had a very good synchronization between model results and the reality. But the key to it was heat losses, and not here roughness and length correction. First heat losses, and if that matches, then so, but that is a user that is doing the design and the operations, and he knows all the people operating the plants, so he's in a very good position to get all the data. Okay, I was now jumping a bit around, but I think it's one of the most important parts to understand how the pressure loss computation is set up and how you can influence those the correction factors and assign correction factors to zones. I go back to the UI and how to use the graphical tools. Let me go back to the construction, and I started here with the wrench tool to access a dialog box. Let me close down the pipe type dialog box. Yeah. Pressure rating means it's the maximum design pressure for this pipe. If you exceed it, the pipe might break. If you exceed it heavily, it will break. And we use this information about the pressure rating to check after the computation if all pipes operate within their design range. So if you, typically these networks are at a certain pressure rating. If it's 16 bars or 25 is quite high.
German using 25
16 bars, I think in most cases 16, yeah. Yeah, yeah.
So many engineers use only use the length correction factor and don't use average, right? Heat transfer correction and for roughness don't use, right?
Yeah, but heat transfer, we use it. You get the data from the pipe vendor. The pipe vendor specifies the insulation, and I know it, for example, for ISO+, they have a catalog, and they give you a value which describes the heat loss over the pipe. And because this is then one of the factors that influences the temperature difference between supply and return. So when you start at the supply station with 110 Celsius degrees and you lose 3 Celsius to the end, and you operate then, let's say at 107 and 50, makes a difference to 110 and 50. So, but I mean, you're right, you can start computation without pressure loss. And once it is working, just add the pressure losses and see how the results will change. If you include the pressure losses, it automatically means that you get higher flows in the network, because without pressure loss, the supply temperature remains on a high level. It's not going down. If it's higher and you change the equation to mass flow is the load divided by Cp times delta t. So it means if the delta t is higher, it's lower mass flow. And when you include the heat loss, you will find then higher mass flow and higher pressure losses. You saw me opening here two other dialog boxes for the zones and for the pipe type. And whenever you focus one of these dialogs, like the pipe type, the dataset selector will show the list of all pipe types. I give the focus to the pipe dialog box, and the lister in the dataset selector adjusts to show all pipes. Similar when I go to zones, the list switches and shows the zones. Instead of navigating via the graphical interface, you can also navigate here via the dataset selector. So if I go to a different pipe, KO31, K23, it will show the data of the selected pipe in this box. So I can this way easily navigate through the data. And similar with the pipe types, DN32, 65, 80, and so on. For the elements that have a graphical representation, you can use this navigation method also to locate an element in the graphics. So when you have the dialog box, let me close zones and pipe types. So with the right click on the pipe, you find in the context menu showing graphic. Up, yep. And when you execute this, it will center the drawing and highlight the pipe. In this case, it's in light blue. Let me zoom in a bit. So this is the pipe we are interested in. And when I select another pipe, right click, showing graphic, it will jump to the location in the graphics. So this way you can easily navigate between graphics to dialog box and dialog box data to graphic. There is a sort of automatic feature in, we call this object tracing or tracking. And when you enable the object tracking, I press the button so it's highlighted. When I now navigate to a different pipe, come on. No, let me see, always center. It will jump to the pipes. If you do not center, that should also be okay. Whenever, it is on the same screen, it will not move the map behind. But if it's in an entire different region and it would not show up, we'll move the map. We do not change scale during the operation. We just jump to the element at the present scale. And this method works with all the network elements. It is not limited to pipes. So when I open, for example, the supply stations, supplies, there is only one. So it immediately, when you focus the dialog box, it jumps to the element and displays it on the in the graphics. Let me zoom out. So this is a feature to quickly investigate an unknown network and to find out where, for example, are the supply stations, where are pumps located, or where is a big consumer. So if I go to the consumers. Another dialog box opens. This is the list of consumers in the system. This one has a load of 200 kilowatts and it's located here. Jump to another one. It's this one here. Maybe it's easier to center it. And this one, yeah, now showing the consumers. I can explain a bit of the graphic symbols we use. Maybe you noticed that whenever I click the consumer, the node is indicated as has a square symbol in the graphics. So those are the nodes that are connected with consumers. If the node symbol is a plain square, a plain circle, it is just a node that is connected to pipes. When the node is this pentagon, then it is connected to a supply station as well. So the lines are the pipes, nodes are circles if they are just connected to pipes, they are squares when they are connected to consumer stations, and they are pentagons if there is a supply station connected. The network we are drawing is a top view of the district heating network, and we do not separate the supply and the return network. It's just the top view, and typically you find both elements, supply and return. We have drawing templates that allow you to label and to color code the graphics. And those can be accessed via this toolbox. The drawing templates get names. You are free to choose a name for it and to create as many as you want. And for a drawing template, you can draw at a certain scale. And in this case, the network supply is water. No, sorry, I did not draw network supply. Sorry, I have to. No, let me do this next with the graphics. Let me continue, please, with the dialog boxes to complete this. I opened multiple dialog boxes and showed how to navigate between boxes and how objects can be traced in the graphics. For the consumer dialog box, the labels appear here in blue. I should explain. That is because we created this consumer from customer information. Customer information is more rich than consumer. Consumer is just the point with the demand. For a customer, we additionally have the address information, maybe phone numbers, and so on. Yeah, you here on the consumer, we have a top page customer. Do you have a network with such customer? Okay, perfect. So you can, and by double clicking it, I can open the customer data. And customer data can separate or distinguish between heating and hot water generation, or maybe even ventilation if it's there. So you can split the demand into several parts if you want. And under user-defined data, you have more information like first name, last name, house number, postal code, and yeah, whatsoever. These are just informational fields. They are not required for the hydraulics at all. It is not required to use the customer data, but we learned from our users that they often have this information available and they want to use it.
What does it mean? The customer data in the customer data. What does it mean? The tap water.
The tap water is for hot water preparation for shower. It's the warm water in the house. So you have the heating part. It's mostly used in winter times, but not in summer times. But you always need throughout the entire year the hot water preparation. Yeah. In your hotel now, there is no heating. It's warm outside, but you can shower in the morning with hot water. So tap water, hot water. It's this is the yeah. It's that you get warm water in your house.
It's like an accumulator, right?
Um, yes, right. Yes, right. Yes, there is an accumulator in the house, which is a large bottle with the hot water, and you keep it at the higher temperature, even during summer times. Right. Okay, with the dialog boxes, I explained we have with the right-click menu, you get a dialog box context menu. When you click here on empty space in the dialog box, you get the dialog box context menu. It allows to copy, delete, or create a new data set, and to navigate to the first in the list, previous, next. And there you also find the showing graphics. And for connectivity purposes, there is a function reverse connection, which means to switch the start and the end node. The typical operation to create a new pipe is doing it via the graphic tools. It's easiest and safe. You can do it also via the boxes. So when you create a new pipe, it creates a new one. You can do the connectivity here with the dialog boxes, choose your start and end node, but that's really cumbersome to do this. So it is possible, and you can maintain or edit the data. Let me delete this here. The standard way is doing it via graphics. And you had the question at the very beginning, how do I keep the diameter at DN300 when I do the piping for the house stations, for example? And the recommended way for it is when you start with a pipe that is on DN300, or let's say we want to now construct a pipe here with DN50. It splits the pipe and goes here to the end. So let me zoom in a bit. So this pipe is on DN100. The tooltip for the pipe shows the computational results. In the middle, we find a length of 518 meters. The pipe type used here is DN100. And we are going to construct now a pipe that is splitting the DN100 pipe. And we want to use a DN50. Whenever a pipe dialog box is open, it is a template for the pipe we are about to create. So this is now template for the one we construct. When we choose a different one, it uses a different one as template. Template means it takes all data from this pipe. It takes all information from the template except the connectivity and the length. But of course, it takes here it would take the exterior temperature, the price category, if it's supply and return, and most important, it takes the pipe type and the zone information.
So you mean if I want to fix the main pipe, to use the other template, right?
Sorry,
If I want to fix the diameter main pipe.
Yeah.
And I want to design a branch pipe. Use the other template, right?
Sorry, your question was only for design. Okay, that's another story. Okay, now for layout, let me do this here. I start the pipe layout tool. The pipe dialog box is open. When I do the construction, MicroStation opens a so-called tool setting. It is a setting with options for this graphic operation. For different tools have different settings. The setting here is labeled like the construction command. It's for create pipe. So let me show that other tools have other settings. So for create pump, there is only the options open the pump dialog box immediately once the pump has been created. And when you create a pump, when I create it, it allows me to split pipes. When I create a supply station, the options are again different. Some are the same, but for example, when I create a supply, I can additionally create a pump with it. I think we'll do an exercise if you're to show how the graphic tools are working. The objective now was just to show whenever you have such a command, it is worth looking at the associated tool settings. They may give you some assist. In the case of pipe construction, the tool settings give me the opportunity to allow to split pipes. Instead, I can force the tool to only connect existing nodes, which means I cannot start here in the middle and split the pipe. Instead, I would, if I use it this way, allow use existing nodes, I have to start at a node. I cannot do it here. See the small hint at the cursor? It's the forbidden sign. And when I rest on the pipe, it tells me splitting the pipe is not allowed because I set the mode to use existing nodes only. Easiest way is, or for most situations, it is good to allow splitting pipes. And with splitting pipes, I can move onto a pipe and see now there is a cross indicating the split point on the pipe. And the tool setting also tells me what happens when I press the mouse button. Whenever I press the mouse button, it will add a bend to the pipe. And when I drop down here, you find that a control mouse click will create a node. When you click Control Alt, it will create a consumer at the point. So let me start constructing a pipe with 2 bends and a consumer at the end. So I will move to the pipe. I will click, just click, which means it creates a regular node that splits this pipe. Now I will click 2 times to create the bends. One here, say one here. And the final node is a node. Now I want to place a node plus a consumer in this node. I can switch here to consumer, do the click, or a hint is here. The shortcut is Control Alt, mouse click. I will use this method, so Control Alt, mouse click, Control Alt key, left mouse. It will create the node and it will associate a consumer with the node. And now you notice that the pipe dialog box displays the newly created pipe. It's from node K0114 to node K116. It's the connectivity. It's with the same zone and the same pipe type. In the tool, I click the option Continue Next Pipe from End Node, which means the next pipe has already started, and the start node was defined by the end node. So when you do a series of pipes, that's the most convenient way to do it. In MicroStation, you can use the right mouse button to reset an operation. So with a right click, I can do 2 times. I can stop the pipe construction, or you can just create click the pipe creation command again. The right click is important in the following situation. If I construct with a series of bends and I want to remove one of the bends, every right click will remove one of the bends. And when it's the first node and I right click, okay, I remove this one as a start node. Okay, this is for network construction. Let me undo the construction and show a different way to accomplish this. I use now one tool, the pipe tool, to construct, to split the pipe, to do the piping, and to attach a consumer at the end. You can also do it in a different way with a create node tool. So I do a single step, I split the pipe. And I only split the pipe. So create node tool, move on the pipe, want to place the node here. It splits the pipe, we are done. I can then create, for example, the end node in this location. After I created the end node, I can do the piping, starting here, doing bends. Whenever I hit with the mouse key the end node or start node, it will be highlighted to indicate that the next click will snap to it. There is no need to go to the center of the node. You can touch the edge of the node, and when I now click, it snaps to the center and it completes the pipe construction.
Automatically snap. Snap?
Yeah. So when I here move to the node, now pipe construction started. I need a first node, so an existing node is detected, it's highlighted, and click will snap to it, so it snaps and starts at the center. And when I move to a possible end node, the node is highlighted again, and clicking means I accept it as an end node. Of course, the node K120 is not eligible as an end node. In district heating, start and end node are always different. So you cannot connect here back to K120. It's not allowed. And so now I created the node, 2 nodes, the pipe. The final step would be to create a consumer in this point. So with the create consumer tool, okay, it also allows splitting pipes, but I can point to a node. It's highlighted. When I click on it, a consumer will be attached. So now I go again to the whiteboard to explain a bit what you see in the drawing and how that refers to this supply and return network. So we have a top view of the network. So I go to that with the design later. Go back. So you see the supply line. Start a net node. And there is also the return part of the network. With our construction, we do supply and return at the same time. So this is for the node. In one ends here, I created a consumer. The consumer in sisHYD is a real element between with the start and the end node. And because we cannot symbolize both nodes and the consumer in the top view, we said, okay, we use a square to indicate this situation. And when you do a supply station, it's typically in here, and the supply station usually comes with a pump in the supply or in the return. And that is why our supplier construction tool allows to construct, when you click on a node, to construct a pump along with the supply station. So, let me undo the most recent step, that was the consumer creation. So on node K120, with the undo, the consumer will go away. The graphics updates, so this is now a regular node. It is this situation before adding a supply station. So it's just the square symbol. There is only a pipe attached with the node. We can review what is attached with the node. Let's have a look with the added object. I click onto the node, and the node dialog box has one page called Connections. And when I go to the Connections tab, I find that it is connected with a supply pipe, K120, K118, V. That's some, in German it's fall off. That's the V it stands for. And it has a return pipe, K120, K118R. Let's have a look at this node here, which is also a terminal node, but which has a consumer associated. I click on the node and have a look what happens here to the connections. It has the pipe K97 to K99. It's the return pipe, and it's the supply pipe. And additionally, you find the consumer associated in this point. So this is the situation you find on the right side. So when I click the node, the dialog box shows the supply part of the node, the return part, and therefore for two nodes it looks up what is connected to it, and that makes up the list. So it's both nodes, it's this consumer, and it's both pipes. So now let's have a look here at I create a supply now on node K120, and I use the tool to create a pump along with the supply station. So to create the situation we have on the board, it's a pump in the return. So I want to have a pump in the return. I want the supplier, I give it a name, supplier 2. And I click here, I select the node and I click. And let me open dialog boxes, because now a lot of things will happen. And watch what happens here to nodes and supply. It opens additionally the pump, and the symbol changes. Now with one click you created an intermediate node, the pump, the supply. The network elements in the SisHYD have always a start node and an end node. So a pump which connects to a supply station, it needs an intermediate node for the connection. That is why we create in the same spot an additional node, and the node is for the pump the end node. For the supply station, it's the start, and the supply node I clicked onto is the end of the supply station. Let's verify this with the dialog boxes. So we look at the pump. The pump starts at K120, this node, but in the return, that's where the R stands for. The end node is a node we created here, node supply 2. That's the node here in the middle, which was created by the tool. And when you look at the connection list for the node in the middle, it is connected to the supply and it's connected to the pump. And the supply itself, on the right side, it starts at the created intermediate node and it ends at the supply node K120. So we label this node, this one here, K120. V, it's German for supply. So, and this is K120R. In the dialog box, the label is just K120 because we consider it a symmetric node. It is a pair of nodes. The intermediate node got the name of the supply station, supply 2. It's a node that is, let me switch here to the general tab page. That's a node which is only in the return. There is no counterpart in the supply. You can have one, but it would be orphaned with no connection, so we do not need it. And this explains also how the network is modeled in the SisHYD. We have nodes and elements. Elements always have a start and a stop node. And this is very important to create this circular system from supply through consumers via return back to the supply station. And whenever something bad happens with our computation and it cannot compute, the key is often in these situations that you break the loops. And if you shut down these pipes, it is not going to compute. We need the closed loop. And yeah, same with computations. If you operate the supply station but you shut down the pump, you turn it off, it's for the computation like the pump does not exist. You broke the circuit, it's not going to compute. And in most cases, look at the supply stations if the connectivity is right. You can do the connectivity on your own. We recommend the graphical tool because that with the graphical tools it's always okay.
Second, can we have a break?
Yeah, sure.